Okay. I mentioned already that we are looking at a large set of application areas, and I mentioned already the fact that you might wonder why we can actually touch all these different application areas in a single course. For what reason can we describe so many different application areas? Well, we can touch many different application areas because these application areas have a huge set of common characteristics. And I'd like to refer to these common characteristics. The first characteristic is the fact that cyber-physical and embedded systems must be dependable. The key reason is that whatever we do in our information processing part has an immediate impact on the physical environment. So in case we do something wrong, we might cause harm to some objects, we might cause harm to people, and that has to be avoided under all circumstances. So it's not like with office automation, where in case there is a problem with some program, we just start the computer again. It's not like that. We have to make sure there will be no harm caused. And as an indication of that situation, I created that kind of traffic sign there. So cyber-physical and embedded systems must be dependable, and this comes in a variety of flavors and in a variety of aspects. The first aspect is reliability. Reliability refers to the probability of a system working correctly, provided it was working correctly at time t = 0. That means we are considering the probability over time that the system is working. The second aspect is the so-called maintainability, which takes into account that systems might fail, and if they fail, it should be possible to repair these systems, and it shouldn't take too long. So therefore, we are defining maintainability, where maintainability is defined as the probability of a system working correctly d time units after an error occurred. Then, as a third aspect, we have availability. Availability is the probability of a system working at a particular time. So for example, let's suppose that we have a system which very predictively works for 999 hours and then fails for 1 hour and then works again for 909 hours and then fails again. So such a system would have an availability of 99.9%. Furthermore, we have to make sure that these systems are safe. We have to make sure that no harm is caused, and that these systems are secure in the sense that confidential and authentic communication should be established. In this context, I'd like to refer to two citations from a very well-known colleague of TU Vienna. Hermann Koppitz wrote in his very important book, "Even perfectly designed systems can fail if the assumptions about the workload and possible errors turn out to be wrong." So for example, if we assume that a certain condition in the environment will always be met, and if then later this condition is not met, then the system can fail even though it was perfectly designed. So that's something that can always happen. And also referring to Hermann Koppitz, we can state that making a system dependable must not be an afterthought, it must be considered right from the beginning. So it doesn't work if we just make sure that the system works, and once we have designed a working system, we then start to make it reliable. That doesn't work. If we want a reliable system, we have to take that into account right from the beginning, because the physical partitioning, for example, might depend very much on the need to design a reliable system. So that is the first common characteristic. There are some gimmicks there. The second common characteristic refers to the efficiency that we would like to achieve. Cyber-physical and embedded systems should be efficient, and this efficiency, again, has a number of aspects. So for example, if the entire system has to fit onto a single chip, that means if even the code that we would like to run has to be stored on the same chip, then we have to make sure that our system is code size efficient. Furthermore, our system should be runtime efficient. That means of the available processor cycles, we shouldn't waste too many for useless work, but we should make sure that we are using as many as possible of the available processor cycles for useful work. Then also these systems should be weight efficient. I know that if you buy a mobile phone, for example, you're looking at the weight of the mobile phone. So therefore, it's obviously very important that such a system is not much more heavy than what the users would accept. These systems should be cheap. If you buy a new mobile phone, you would like to spend the least amount of money that's possible. Maybe you don't get it for a couple of cents, but nevertheless, you would like to pay very little money for a very advanced system. And for mobile systems, it's very important to be energy efficient, and this applies even to cars, because cars are parked over very long periods, and we have to make sure that there is not a too large energy consumption while such a car is parked. So that's the second common aspect for cyber physical and embedded systems. The need to be energy efficient has some very far-reaching consequences. And this relates, for example, to the type of processing that we can use in such a system. And I'm demonstrating this by using a diagram which is displaying the energy efficiency of different hardware platform technologies. In the vertical dimension, you see the number of operations that we can perform per joule. So that's the energy efficiency of a certain hardware technology. And in the horizontal dimension, you see years, and these years implicitly refer to a particular implementation technology or silicon technology that's available for a particular year. And you can see that for standard processors such as Intel microprocessors, the energy efficiency has improved over the years. But if you look at a particular fabrication technology, let's say you look, for example, at the technology that's available in 2005, you can see that the energy efficiency of these processors is lowest. You get a much better energy efficiency for specialized digital signal processors. You get an even better energy efficiency for field programmable gate arrays, or so-called FPGAs, and you would get the best energy efficiency for a custom integrated circuit called application-specific integrated circuit. Now, if you need to be very energy efficient, then you need to be in this upper right corner of this diagram. I'm calling this upper right corner the sweet spot of this diagram. And the overall goal is to come to this sweet spot of this diagram, which means that these standard processors, for example, they cannot be used in systems that have to be energy efficient. And you have to live with the technology that's available for this sweet spot of this diagram up there. So that was another common characteristic for cyber physical and embedded systems. A third common characteristic is the fact that we are using these systems very frequently in a so-called hardware loop. And this hardware loop starts with the physical environment. To the physical environment, we attach sensors. These sensors are computing certain physical quantities. And typically, we need to convert these physical quantities to digital values, because in many cases, actually most cases, these sensors will be generating analog values. So we need to convert them to digital values, because the computers that we work with these days are almost all digital computers. There are hardly any analog computers left. And these computers will then do some information processing. The result might be displayed in some digital display, also possibly some analog display. And then using some actuators, we can have an impact on the physical environment. But since these actuators in most of the cases are also analog actuators, we might need again a conversion back from the digital domain to the analog domain. And these loops we will find very frequently. Therefore, it does make a lot of sense to talk about cyber-physical systems because we see this very strong link to the physical environment. Another common characteristic of cyber and cyber-physical and embedded systems is the fact that we have, again, a consequence of the direct interface between information processing and this physical environment. That means we have to respect time as a physical quantity, and that means cyber-physical systems must meet real-time constraints. In this context, it makes sense to define the term real-time system. A real-time system is a system that must react to stimuli from the controlled object or the operator within a time interval dictated by that environment. That means we have a certain time until which we have to finish all the computations, and we have to make sure that we really have finished all the computations until a certain time. In this context, we are frequently distinguishing between different types of time constraints. Real-time constraints are called hard real-time constraints. If not meeting such a constraint could result in a catastrophe. And all other time constraints are called soft time constraints. Sometimes people also define the term firm real-time constraint. That is a time constraint that is somewhere between a hard real-time constraint and a soft real-time constraint. Again, citing from Hermann Koppitz, I'd like to mention that guaranteed system responses must be explained without statistical arguments. That means it's not acceptable that we try to prove the reliability of a system by running, let's say, 99 experiments. And if we meet all the time constraints for these 99 experiments, we conclude that we are meeting the time constraints in 99% of all the cases. That would be a completely wrong approach for several reasons. So whenever we try to figure out whether a system meets its time constraints, we should do this without statistical arguments. Okay. Looking at this last slide, we might be a little bit confused because there might be the impression that real-time systems and cyber-physical systems are actually denoting the same thing. So do they really denote exactly the same thing? Well, they most of the time denote very similar things, but there are a few exceptions. There are a few exceptions which motivate the distinction between real-time systems, embedded systems, and cyber-physical systems. There are some embedded systems for which real-time behavior is less important, such as smartphones. For smartphones, there are only very few areas where real-time behavior is extremely important. In some parts of the communication protocols, real-time behavior is important, but otherwise these smartphones don't have to consider real-time constraints. For cyber-physical systems, that means for systems that are really integrated into the physical environment, real-time behavior is essential, and therefore real-time systems and cyber-physical systems are very similar. But we have to stress the fact that for the cyber-physical system, we expect that the physical environment is also part of the model that we are considering. In this context, there is also a term that is sometimes used by some people. People also are talking about reactive and hybrid systems. A reactive system is a system which is in continual interaction with its environment and executes at a pace determined by that environment. So we are referring to, for example, control systems that are permanently connected to the physical environment, and for historic reasons these are frequently called reactive systems. For such reactive systems, the behavior depends on the input and the current state, which means that automata models are appropriate models for such systems. Just looking at functions that could possibly be computed is not enough, because we really have to consider the state as well. It's not sufficient just to figure out whether a certain function is computable. Also for these systems, it's a very common characteristic that we have analog and digital parts. We have seen this already from the slide showing the hardware loop. In that hardware loop, we typically find analog parts, and in the information processing, we will typically be using digital components. Another common characteristic of these terms is the fact that these systems are in many of the cases dedicated towards a particular application, and that we can use this specialization towards a particular application to really design a very efficient system and to make sure that we only need the minimum number of resources. So for example, if we design a car, we would add additional information processing systems only in a very limited way. So we will be adding maybe some simple devices, but we are not changing the information processing for the safety critical part. Also for these systems, we are typically using a dedicated user interface, so no mouse, no keyboard, no screen. But I have to admit that this situation is slowly changing. If you look at the very large seagoing vessels, you might have observed that these very large ships, they are by now controlled with a joystick, and there is no wheel anymore. So the wheel might still be there, but it's just for decoration. So therefore, the situation is slowly changing a little, and we are also seeing cars being designed so that limited changes are feasible, that it's possible to have certain add-ons there. Another characteristic is the fact that cyber, physical, and embedded systems are underrepresented in teaching and public discussions. So typically people talk in magazine ads about the most recent smartphone, but you will hardly see any very recent embedded chip to be advertised there in such an ad. Most of the cyber, physical, and embedded systems will have the majority of all these characteristics, and therefore we could also define the term embedded system in a somewhat different way. We could say information processing systems that have most of the above characteristics are called embedded systems. That would be a different way of defining the term embedded systems. Now, I mentioned earlier that we are having applications, potential applications of our fundamental technologies in many different application areas, and the fact that this is feasible is due to this observation. It's due to the observation that these different application areas have so many common characteristics. Otherwise, we would need a separate course on automotive electronics, a separate course on avionics, etc. There might still be more specialized courses for these areas, but an introductory course can cover a larger set of application areas. Okay, so coming towards the end of this course, I'd like to mention the textbooks that are available to us for this course. Fortunately, there is a very large set of textbooks that you can use when you want to read something about the topics covered in this course. The first textbook is this one. It looks like that, and it has this front cover. It is an English book that came out in 2003, and if we look a little more closely, we can see who the author is. If you don't like that book, you can still use another book. It looks like that. It came out in 2006, in late 2006 or early 2007. If we look a little more closely, we can figure out who the author is. But if it requires the reading of German. If you don't like that one, you can use another one. You can use that one. If that book came out in 2006, if you look a little more closely, you can see who the author is. If you don't like that one, you can still use another one. It's that one. But for that one, you would need to be able to read Karelian. It's written in Macedonian. If you look a little more closely, you can see who the author is. Well, I don't have a magnifying glass in that case. And finally, there is a sixth book that you could use as well. It's the Red Book. This is the most recent edition of the book. It came out in late 2010, early 2011. Right now, it's available only in English. Michael is working on getting the German edition done, and the contract has been signed for the Chinese edition. There will be an edition in simplified Chinese. I'm not sure at what point in time that version will come out. So these are the options that you have for reading something about the topics discussed in this course. Also, you would possibly like to get access to slides. There is one general website where all the information about material linked to the book is available. But then on top of that, we are making the slides also available under EWS, which is a system where we can store material that is used within the course, and there are separate folders for the PDF and the PowerPoint version. Master format in both cases is the PowerPoint version, and that means whenever there is some layout problem, it's possibly due to the generation of PDF. The PowerPoint is the master document. Okay, and this is the summary for today's lecture. I have motivated this course by having a look at the future of information technology. I have defined embedded and cyber-physical systems. I mentioned the growing importance of embedded and cyber-physical systems. We looked at the different application areas and examples. We used them to demonstrate the wide range of applications of the techniques that you will be learning in this course. We briefly looked at the curriculum. I motivated the wide scope for the curriculum. And finally, we looked at common characteristics. So this concludes my part. Thank you very much for your attention.